So in this video, I'm going to look at transforming sine and cosine graphs. And I like to do the transformations of them based on the general transformation pattern that's given in the methods course outline in the study design, and that's this format here. And so for any of the functions that we've been working with, you just replace f of x with whatever function it is. The a value out the front dilates vertically. It either stretches or compresses vertically by a factor of a, and if it's negative, it reflects across the x-axis. And it's really important when you're writing your answers in the exam that you get the correct language for reflections. So reflections are across an x-axis or reflection in the x-axis. Don't say a reflection of the x-axis, so make sure that you get that correct. The n value is a dilation, which is a horizontal dilation, either a stretch or a compression by a factor of 1 on n. If it's negative value, you reflect across the x-axis. The positive b here is a translation negative b units in the direction of the x-axis, and finally the plus c on the end is a vertical translation of c units. And so if you follow the mapping of x and y through this function, what you get is that x maps to x on n minus b, and that y maps to ay plus c. And if you want to think about it, the x values in a slightly different way, you can think about it as 1 on n times x minus b. So let's have a look at what these changes and these transformations using these ideas have on the properties of our sine and cos curve. Okay, so let's have a look at what happens when we change the values of a, n, b and c. Now unfortunately in this little interactive they've left the points labelled as a, c and b. Now a, c and b here have no correlation with a, c and b here. So these are just going to be points, a blue point, a red point and a green point that I'm going to pick up and move in a minute, and we're going to see what happens to the value of the function here. And so what we're going to keep a track of, here's our sine curve and here's our cos curve here. We're going to keep a track of what's happening with the properties of these graphs. So the range, initially our range is for an untransformed graph is from -1 to 1. The period is 2 pi, the amplitude is 1 and the mean value is 0. So we're going to have a look and see how these change when we change these particular values. So let's start with this a value here at the start, which dilates vertically. And so to do a vertical dilation, I need to grab the red point at the top, the point C, and move it up and down. Now it's going to click by whole units, it's not going to scroll nicely. So you can see that I am stretching the graph vertically and compressing the graph vertically. And what's actually changing is the height of those peaks. And the height of those peaks we call the amplitude. And so if I dilate it by a factor of 2, you can see in the formula in the yellow box that it's now the a value in front of sine is 2. So the stretch is 2, and what it's doing now, the amplitude of that graph, if you have a look, the amplitude of the graph here is 2 and that value is 2. If I grab this point again and stretch it again up to 3, you can see the amplitude's changed to 3, the a value is 3. If I increase that a value in the function, the value in front of sine, to 5, you can see that the amplitude is changed by 5. And also the maximum value of 4, I meant to go to 5. There we go, now that's 5. The maximum value is 5 and the minimum value is -5 for that graph. So our maximum value is 5 and our minimum value is 5. So what this value at the front is doing is it's changing our range and it's changing our amplitude. And our amplitude is changing by whatever this factor A is here. And so our amplitude for our graph is now A. So this A in the formula here tells us our amplitude. It also tells us what our maximum and minimum values are going to be, so what our range is going to be. And our range is also getting, both of these values are getting multiplied by A. But we're going to leave that just for the minute. And so what I want to look at as well is what happens if we stick with changes to Y value. What happens if I move the blue dot in the center of the graph and I move it up 1 unit? You can see that the mean value has shifted up 1 and the maximum value has also shifted up 1, but the amplitude has remained the same. So you can see that the maximum value now is the mean value plus the amplitude, so that 1 plus the amplitude, and that the minimum value is the mean value minus the amplitude. And so this plus C on the end changes our mean value, and it also changes our range. So our range becomes the C plus the amplitude and C minus the amplitude. Oops, I got those round the wrong way. So how do you go about graphing something like this? We use what we know about the 2 at the front and the other values, the effect that they have on the graph to help us. So let's look at the 2 front and end numbers. They're the changes to Y. The 2 at the front tells us that the amplitude is going to be 2, and the 1 at the end tells us that the mean value is going to be 1. So the centre of the graph shifted up 1. The 3 tells us that the period is going to be changed because the 3 represents a dilation by a factor of 1/3 from the y-axis. So our period is 2 pi on 3. Our period is always 2 pi on whatever that n value is there. And then finally, our sine curve is going to start at pi on 4 in the positive direction of the x, from the x-axis. So it's actually going to start a little bit over to the right. It's being translated right. But that doesn't help us to graph this thing. So what I'm going to do is teach you a technique that starts with the main 5 points on the sine and cos curve and transforms those points using our mapping pattern from our general function equation. So let me draw it for you. So here is our sine curve, and these are the 5 major points that we're going to track, and we're going to change their coordinates using this mapping pattern here. So the first point is 0, 0. So I've got 0, 0 here. Our end point is 2 pi and 0. So 2 pi and 0. And from there we can fill the table in. Halfway between 0 and 2 pi is the value of pi. Halfway between 0 and pi is pi on 2, and this one's 3 pi on 2. And our y values for our sine curve go from 0 to 1. So in our box they go from 0 to 1, then to 0 to -1 and 0. And so this is the table of the 5 main points for sine of x, and we're going to use this over and over again to do our transformations. So let's fill in what our transformations need to be for our x values. We're going to put them up here. From our equation, we've got our n value is 3. Our b value is in fact minus pi on 4. So we'll be putting minus pi on 4. And our a value is 2 and our c value is 1. So that means that our mapping is now x on 3 minus pi on 4. So that becomes x on 3 plus pi on 4, and our y values become 2y plus 1. So let's make the changes to y here. So we're going to do 2y plus 1 for 0. So 2 times 0 is 0, plus 1 is 1. Let's do the next one. 2 times 1 is 2, plus 1 is 3. The next one is 1 again. The next one, 2 times minus 1 is minus 2, plus 1 is minus 1. And then 2 times 0 plus 1 is 1. And so these are our new y values. Let's do the same for our x values. Now these can get a little bit messy, so I might just zoom in. And give myself some space to write. So the first thing we do is we substitute our x value into our formula, our transformed formula for x. So we've got 0 divided by 3 plus pi on 4. 0 divided by 3 is 0 plus pi on 4. That gives us pi on 4 as our first x value. So let's do the same with the next x value. So it's going to be divided by 3, and this time our value is pi on 2. Divide that by 3 plus pi on 4. So dividing pi on 2 by 3 is the same as saying pi on 2 times by a third. I can squeeze that in there. Plus pi on 4. So that gives us pi on 6 plus pi on 4, and you can see what I mean by messy. So these need to have the same denominator. So I'll turn them both into 12ths. So that gives me 2 12ths, 2 pi on 12, plus 3 pi on 12, to give me 5 pi on 12. See what I mean by messy? So for the next one, we put pi over 3, we add pi on 4 to it. Our fractions need the same denominators to add them, so I'll change them both into 12ths. So multiply the first fraction top and bottom by 4, so that's 4 pi on 12, plus second fraction top and bottom by 3, so 3 pi on 12, and that gives us a total of 7 pi on 12. So we had pi on 4, 5 pi on 12, that should be 12, and 7 pi on 12. Often at this stage you can just look for a pattern, an increasing pattern from one x value to the next, because on the graph of the sine function the x values are equally spaced. And so what I'm going to do is I'm going to have a look at this first x value and change it so my second two are both out of 12, they're 12ths. So if I'm going to write this as 12ths, this is going to be multiply top and bottom by 3 pi over 12. And what you've got is, let me just grab this here, you've got 3 pi over 12, 5 pi over 12, 7 pi over 12. So what's happening is as we go from left to right, we are adding 2 pi over 12. So the next one here will be 9 pi over 12, and the one after that, 11 pi over 12. We can check that by working it out, and I'll do it for you now. And as you can see, if you plug the numbers into our transformed x value, you get 9 pi on 12 and 11 pi on 12 as we predicted. And you can use this constant change from one x value to the other to save you time generating your x positions for our transformed functions. So now we've got our transformed x values and our transformed y values. Now we just need to plot them on the graph. And so to do this, we need a graph that you're able to read. So I'll just write it out for you again, and then we'll graph it. So here's our tidied up table, and you'll notice that I've left our x values as unsimplified fractions. The reason for that is that sometimes we need to use this adding of a constant amount, in this case 2 pi on 12, to each of these values to extend the graph beyond the 5 points that we've got onto the next point. So because we know that the sine curves continue and continue and continue, and so we can just keep on adding 2 pi on 12 to each of our values and generate more values there. And for this one here, for the one on the y values here, we just follow this idea that we've got our three numbers here, 3, 1 and -1, and that they just keep the pattern of increase to 3 and then decrease to -1, increase to 3 and decrease to -1. So if we followed that pattern, our next few values go, they start with 1, 3, 1, -1, 1, 3, 3, 1, -1, 1, 3, 1, -1, 1, 3, and you on and on and on it goes for however many of these new ones you want to generate. So to sketch the graph, our mean value is 3. This 3 is 1. And so I'm going to put a dotted line, and that's going to be our mean value. And our shape of our curve is a sine curve, so we're going to go up and down and up. And I'm going to label the 5 points that are on here. So we know from our graph at the start, our analysis at the start, that our mean value is 1 and our amplitude is 2. That means that our mean value is a line y is equal to 1, and if our amplitude is 2, and this is number 1, then this goes down below the x-axis. And so I'm going to pop the x-axis in blue as an x-axis. We also know from our original graph up here that the starting position has been moved to the right, pi on 4, and so our starting point here is to the right of the y-axis, so I'm going to pop that in. Now I'm going to use my values from the table to mark in the coordinates for each of the points. So this first point here is an x-coordinate of 3 pi on 12. The next one has an x-coordinate of 5 pi on 12, and so on and so on. If you want to mark them in, that's 11 pi on 12. In terms of marking in your X-intercepts, that's for exercise 6E. But this is enough to mark these points in, and so if I want to put this is the point 5 pi on 12, 3, and this is the point here 9 pi on 12, -1. If you want to tidy up the ones that can simplify, then you can do that at the end. Now, in terms of the level of difficulty of this question, this is one of the most difficult questions that you would ever get asked to do. In most cases, you're asked to sketch stuff where you don't have a horizontal translation and you don't have a vertical translation. And so for exercise 6D, 6F, and 6D and 6F, you don't get these problem ones. So in summary, to sketch a transformed circular function, the first thing you need to do is identify the transformations and what effect it has on the properties of the graph, like the amplitude, the mean value, what the period will become, where the graph of the function starts, that starting point for 0, and what the range will be, what the maximum value and the minimum value will be for that particular graph. Then what you need to do is you need to draw a table of values for sine or cos, and the basics of the table are here. You can fill in the rest. My suggestion is that you memorize those tables there, and then add on 2 new rows, an x dashed and a y dashed row, where you do the transformations to x and y that are shown here. And remember, if you're working with your x1s, one of the best hints, sorry, I keep trying to shrink that, it's not working. One of the best hints is to keep all the values that you're getting with the same denominator, all the fractions with the same denominator, and look for a constant increase. That can help save a lot of time doing all of those calculations that we did before. So always look for your constant increase. It's always there. Okay, and then plot the points x dashed and y dashed from your table, and then label points if you need to, and if needed, find the x-intercepts for the graph by solving the equation. So let the formula equal to 0 and then solve it for x. And if you need some help with that, I've got a video 6E called Solving Trig Equations, and you can have a look at that video and it will show you how to solve trig equations. I have a follow-up video in which I'll show you how to sketch graphs of transformed functions with restricted domains, so how to deal with endpoints, and I'll do another couple of examples of this process of sketching transformed graphs. Thanks for watching.